Okay, hey, welcome. This is my first video solution from chapter 25. So let me put here chapter 25. And I was asked to try number 9 here. So, all right, let's give number 9 here a shot. And as I read it, it says here, an insulating rod having a linear charge density lambda of 40 microcoulombs per meter and a linear mass density mu of 0.1 kilograms per meter is released from rest in an electric field E of 100 volts per meter. Now, let me pause right there because there are two things that probably should be pointed out that are important. Maybe it's background information, but you might have overlooked it as you were doing the lecture material. And the first one really was kind of this diagram I was trying to say is, why do we care about this thing called potential? And hopefully you saw two reasons for it. The first reason was it could lead to the idea of potential energy, and potential energy with conservation of energy leads to kinetic energy, which leads to speed. So that's one of the approaches. But a second one would be then taking the derivative. And you see that in this equation, the change in the potential is negative the integral of the electric field, on some distance. So as you move from one position to another, so you're at position A and you move to position B, if you add up that electric field, that is, if you integrate it, you get the negative of the change in the potential. Of course, that comes into the potential energy here. And so more on that in a minute here. But what that means then is the reverse is also true. To get the electric field, we'd have to undo the integral, and that means we have to take the derivative, and then that can give us to the electric field. And so the two reasons we care about the potential is you'll see in these series of problems, and just kind of looking at the problems, it looks like just on that same page, 29, it's kind of hard to read. Is that a 30 or a 31? And then 32, I think it's a 31. Each of those are really kind of going this direction. Use the potential, take its derivative, and get the electric field. And then the other thing I wanted to point out is kind of the units here up until this chapter. You might even say this chapter, we're learning a third way to get the electric field. The first way to get the electric field was Coulomb's law in chapter 23, then Gauss's law in 24, and now we're learning another way. It's not the main part, or maybe it's just as equal. It's 50% of the chapter. From potential, you can get electric field, but from potential, you could also get speed of moving objects, and we can get our Physics 121 going here. And I say that because the units for the electric field, we've been doing newtons per coulomb, and that hasn't changed at all. But if you, and you can see it better in this equation, but let me just keep focusing on here. If I label this, say, with a meter over a meter, then in the top here, this is a joule, okay, Newton times a meter is a joule, and a joule per coulomb is our unit of volt. So a Newton per meter is the same as a volt per meter, and so you might not have caught that, but as I read the problem, it stood out to me because it said the electric field was 100 volts per meter. And so you could interpret that as 100 newtons per coulomb, that's fine, or you could interpret that as 100 volts per meter. They're the same thing. And if you're looking at forces, this is probably a better interpretation. But if you're looking at potentials, this is probably a better. This means if you would move 1 meter, and the field didn't change during that 1 meter, okay, but if you were to move 1 meter, you would change by 100 volts. There's a 100 volts per meter. And that works out really well in this equation. You can see it better here because you know this is supposed to come out in volts. So if this is written in volts per meter, then you're multiplied by meter. That would cancel and you'd get volts. So if you're dealing with the electric fields and potentials here, it's probably better to use units of volt per meter. And that's what we have, and so we will. But in case you missed that, know that a volt per meter and a Newton per coulomb are two options here of labeling the electric field. All right, well, that's going to make the problem then kind of long, but that's a little background, and let me try again here. All right, so chapter 25, number 9. And as I already read, we've got a rod, we've got a charge density, we've got a mass density, or it's in an electric field. And it says here now, the electric field is perpendicular to the rod as shown in the figure. So the figure looks a little bit like this. The rod is this way, and the field is this way. Okay, so as I said, the electric field is perpendicular to the rod. It says, determine the speed of the rod after it has traveled 2 meters. All right, so for the sake of a picture, they don't really say whether the rod is positive or negative. And if it will matter, I don't think it will, but I'll go ahead and put a positive. Maybe even ask what happens if it was negative. But if it was positive, it would be pushed this way in the direction of the field. Of course, if it was negative, it would go the other way. And so in my picture, I'll just say it moved 2 meters. But using our conservation of energy, so going back to Physics 121, we say the energy you start with is equal to the energy you end with. We could write that as initial kinetic and initial potential must equal to final kinetic plus final potential. For problems like this, I like to write it this way. I like to move the kinetic energies over here, and I get final minus initial. And then potential energy move over to here, because this then is the change in kinetic energy. This is not quite the change in potential. It would have to be final minus the initial. It's reversed, so it's the negative of it. And so instead of saying the starting energy equals the ending energy, I'm going to say this. I'm going to say the change or negative of the change in potential energy is equal to the change in kinetic energy. And since buried inside here is speed, and that is the question, right? A is determine the speed. I'll get there by coming over to here and getting the change in potential and put a negative in front of it. And so the change in potential is the charge times the change in the voltage. And so finally, we're getting to the heart of this problem is how do I get the change in the voltage? And there are really 2 good ways to get to the change in the voltage. One of them is to do something along this line that if you know the potential is made up from some charges, you can add all them up, and so that's a good technique. Now, unfortunately, in this problem, that will not serve us well at all. Maybe I better put a page 1 here, because we don't know the distribution of the charges. I mean, we know it's an electric field that is uniform here. And I suppose we could read into the problem and say, all right, we know from the last chapter that uniform electric fields are made from, or one way to make them, from these parallel plates. So we might say this is a rod between 2 parallel plates, and so to get the potential at these 2 points, we would add these all up. But that seems like the hard way to go, when it would be so easy to come back and just say the definition of the change in the potential is just adding up the electric field. And the change then would go from A to B. And so if we say this is point A, and then it moves the 2 meters to point B, we could actually do this integration. So this would be minus. And if we're going from here to here, we're going with the field. That's important because the first thing to do is to take this dot product, which is cosine of the angle between the field and the direction you are moving, or the direction you are doing the integral. And so I'm just going to go that direction. So that's 0. And of course, the other thing is the electric field. Of course, once I took the dot product, this is the magnitude of the electric field. So there's the magnitude of the electric field. I'll leave the negative here. And then I've just got this integral from a to b of dr. And that one, I'm hoping you can see, we don't even have to really do that. That's just how far did you move, dr. And so that's the 2 meters. So this is minus the electric field times the 2 meters, or 100 volts per meter, as they said was the strength of the field. And then moving it 2 meters would be a decrease, negative 200 volts. So that's the change as it goes from here to here. It's a decrease of 200 volts. By the way, if this rod had been a negative, then of course it would have moved that way. It still would have been 2 meters, okay. But it would move then opposite of the direction of the field for a negative charge. And that means down here, instead of having 0 degrees, we would have 180 degrees, which would have given a negative. And so we would have had an increase of 200 volts. Okay? And so this direction is a decrease in potential with the field, and this is an increase in potential. And hopefully you caught that in the lecture, that as you move, if we imagine this field was created by these parallel plates, as we move closer to positive ones, the potential goes up. So this way goes up 200 volts, and this way goes down 200 volts. Now, that wouldn't change the answer to the speed. They would still be going the same speed, just the negative would be going that way, and the positive would be going that way, as you'll see as we continue on with the mathematics here. Now, the change in potential energy then would be the charge you place there times this change in voltage. Now, this one's worth discussing because it also is really kind of the answer to later on where they go B. What if how does your answer in part A change if the electric field is not perpendicular to the rod? So let me be careful here. You might do something like this. You might come back here and say, well, let's look at this rod as a little chunk of charge here, and then another chunk of charge here, and another chunk of charge here. And then as it moves, of course, they each move 2 meters. And so this would still be the same, or this we already did as a negative 200 meters. And then you might, I don't know if you would want to call this Q sub I for a second. And just say, okay, let's just take one of these chunks here and call it Q sub I. And then that would get you the change in potential of just that ith piece. But then to get the total, we would say, add up all the pieces. And so this would say, add up all the Q sub i's, each changing by 200 volts. And because the negative 200 volts then would be the same in each term, we would just have the sum of the QIs. And that right there, then, the sum of the QIs would be, I'll just call it capital Q, for what's on that rod. And so this then really is negative 200 volts multiplied by the Q on the rod. Now, we don't completely know that. That might make it a little bit harder. If we say that the rod has a length of little l, then we could write this as negative 200 volts, and then let's write this as lambda times little l. This is the charge per length, and then multiplied by the length. And so that's the change in the potential energy of it. So if we take the negative of the change in potential energy, that's a positive. So in other words, the change in kinetic energy is positive. It increased. Exactly. And that means it went faster. And of course, not a surprise. Going back to just forces, not energy, but forces, we would have said the forces in this direction, and it would make it go faster and faster and faster and faster and faster and make it accelerate. In fact, now that I think about it, we could have even done that. We could have calculated the acceleration and got the speed after 2 meters, and not use the energy approach. Maybe it would have been easier. We can just do Newton's second law. But that only comes out easy because the field is uniform. So, yeah, now I second guess myself. Maybe I should have just done Newton's second law, and it would have been an easier approach. But I like the energy one because we seldom get uniform fields. And once we get a non-uniform electric field, then we have a non-uniform acceleration. And getting the speed that way is not easy. So it's better usually in those cases to do energy. So I'm going to continue to use energy here. All right, so then this would say it is 1/2 the mass times the final speed squared. And I hope you can kind of differentiate in my little drawings here. That's supposed to be a lowercase v because that's speed. And then 1/2 the mass times the initial speed squared. And did it say it started at rest? That's why I have a linear charge density there it is, released from rest. So I can cross that term out. The initial speed is 0, okay. And then the mass. And now again, kind of like the charge, we don't really know the mass, but we know the mass density. So if we take the mu and multiply by L, we would have the mass, and then we would have final speed squared. So that's what we're looking for. And then over here is the plus 200. And if you let me drop the units of volt here for a second, this would be a lambda and an L. And then that's where, and good, I was getting a little worried. I was trying to figure out if the L was important here. Turns out it's not. And then I can get the speed. So if I bring this 2 over to here, this is 2 times 200. And then the lambda, as they said, is the 40 microcoulombs. Good. Bring the mu over. That's the 0.1 kilogram per meter. And then that would be the final speed squared. So, grabbing a calculator, I can go 2 times 200 times 40 micro divided by 0.1, and then taking the square roots of that answer is 0.4. So 0.4, and if we follow through our units, we'll get meters per second, and maybe I should. This right here would be a volt, which remember is a joule per coulomb. So I'll do that. This was the charge density, so that's coulombs per meter. And then this down here is the mass density, and so that is kilograms per meter. So the joules cancel off. I'm sorry, the coulombs cancel off, the meters cancel off, and you're left with a joule over a kilogram. Now remember, a joule is a Newton times a meter, and a Newton is a kilogram meter per second squared. So with that other meter, it'd be squared, and with that kilogram down here, would cancel off your kilograms. So you have meters squared over seconds squared, which when I took the square root, gave me meters per second. So yes, the units work out well also. Now, B real quickly then, I know I've talked for a while, is nice because let me draw a picture. Maybe I'll still make the field go this way. So here's the field. But now they say the rod is not perpendicular to the field. Okay, but if you think about these as again, this rod made out of a bunch of little pieces of charge, like we were kind of discussing up here, that's made out of an individual piece. We'll call it Q sub I. Q sub I, all of these individual Q sub I's would be pushed in the direction of the field, so it would still move this way. And so when you say it moves 2 meters, this top part would move over to here 2 meters, and this bottom part would move over to here 2 meters. They would each move 2 meters. And this little piece would then have a change in potential of the negative 200 volts. It would move 2 meters. Now, this would also move 2 meters. And so that would be, again, a negative 200 volts. And so even though they're not at the same spot, that was this whole idea of doing this integral there, it's still going to be at a distance of 2 meters. And this integral right here says as long as it moves 2 meters, it doesn't matter if it's from 0 to 2 or 1 to 3 or 2 to 4 or 3 to 5, as long as it moves 2 meters. And so each of these pieces move 2 meters, although maybe you'll say this one moved 0 to 2, where now that we have it angled, maybe this moves 1 to 3. But it's still all the same. And so that's just a long way of saying it's still going to be the same here. And so we come out to be the same. All right. Hope that helped.